is e to the 0, which is 1, plus e to the minus t squared, which is e to the minus 2t. In other words, putting this all together, the square of c is e to the 2t plus twice 1, which is 2, plus e to the minus 2t. Similarly, when we square s, we get exactly the same thing, only with a minus 2 as the middle term rather than a plus 2. Well, now we look at c squared and s squared, and just by looking at this expression, any hope that c squared plus s squared will give us a nice identity should vanish, because you see, if you add these, you're going to get an e to the 2t term in here, in fact twice e to the 2t. Here you'll get twice e to the minus 2t, and only the 2 and the minus 2 will drop out. On the other hand, should you elect to subtract s squared from c squared, the e to the 2t terms cancel, the e to the minus 2t term cancels, and we wind up with what? C squared minus s squared is identically 4. And by the way, notice up to this point, no use of the word hyperbola. Okay? However, if you think of the so-called unit hyperbola, the one for which x squared minus y squared is 1, notice that c squared minus s squared equals 4 almost has that form. Well, it has the form. All that's spoiling it is the 4 on this side. Now, you could pretend the 4 was a 1, but that would be cheating. What we do instead is just divide both sides of this equation by 4, observing that c squared t over 4 is just c of t over 2 squared. S squared t over 4 is just s of t over 2 squared. In other words, dividing through by 4, this equation can be put into this form. And now you see we satisfy the basic hyperbolic identity of this squared minus this squared equals 1. By the way, since the c's and the s's may not seem familiar to us, what we can do is what? Go back to the basic definition. C of t meant e to the t plus e to the minus t. Therefore, half of c of t is e to the t plus e to the minus t over 2. S of t was e to the t minus e to the minus t. Therefore, s of t over 2 is e to the t minus e to the minus t over 2. And again, the reason I bring this out is that in most textbooks, they simply define the hyperbolic functions this way. I find it a poor motivation. I don't find it easy to motivate where out of the clear blue sky you bring in a 2 in the denominator. All I want you to see in terms of motivating what's going on so far is that if I just defined a function to be e of t plus e to the minus t, and another one to be e of t minus e to the minus t, I could have shown that the first squared minus the second squared was 4, and the motivation of putting the 2 in the denominator is for no greater reason than to help us satisfy the equation x squared minus y squared equals 1. In fact, this is now the connection between what we were doing a few minutes ago and what we're doing now. Namely, if I now call this cosh t, and I call this sinh t, do I get my basic hyperbola? Namely, suppose I take a curve whose equation is given parametrically by x equal cosh t and y equal sinh t. Okay? Where cosh and sinh are now defined as over here without any reference to the hyperbola, in the same way that we could define the circular functions in terms of calculus without having to appeal to the circle. What I'm saying is, suppose we had never mentioned the word hyperbolic function up to now. We have developed a function called cosh t, a function called sinh t, just from these two relationships here. If I eliminate the parameter t here, namely if I square both sides of this equation, of each equation, and subtract, I get x squared minus y squared is cosh squared t minus sinh squared t, but that I already saw is 1. In other words, this parametrically gives us the hyperbola x squared minus y squared equals 1. By the way, let's make another observation. Notice that the exponential can never be negative. See, e to the minus t is 1 over e to the t, which is still positive. Notice that the cosh can never be negative. See, e to the t is a positive number, e to the minus t is a positive number. Therefore, notice that in this particular relationship, not only is the curve given by x squared minus y squared equals 1, but since the cosh can never be negative, it's also characterized by x is positive. And you see, that tells us what? That what we're getting this way is not the entire hyperbola, but just the branch for which x is positive, which is exactly what we were talking about earlier in the lesson. Again, I leave further details of this to the exercises. All I want to do in today's lesson is to get the flavor of what's going on, how we can invent the hyperbolic functions without reference to a hyperbola until we're all done. See, I hope you see this juxtaposition. We've done two things here. One is we started with the hyperbola and showed how we could invent this construction. The other is we started with the exponential and showed how we could construct two functions of the exponential which had the property that they could be identified with the thing that was called the hyperbolic cosine and the hyperbolic sine. In other words, we could take either of the two approaches and derive the other. But I don't want to put in all of those details here. Okay? At any rate, to show you